the shortest route. This presentation will focus more on the algorithm I wrote to find the shortest way out of the maze. So our solution for the maze tracking is we have 3 distance sensors on the robot, one facing forward, one looking to the right, and one looking to the left. For navigating to the object, we always follow the right wall. And then every decision that the robot makes is recorded into an array. Then once we get to the object, we put all of those decisions, the array, into the algorithm, and then that algorithm will then give us the fastest way out of the maze. Now, unfortunately, due to PC to Mac issues, I can't show the short video of the robot. So what does the robot actually record? Well, it records 4 different things while going through the maze. It records an L into the array when the robot turns to the left, as seen in this example here. It records an R when the robot turns right, as seen in these next 2 examples. It records an I, which stands for an ignore, which is when it sees a left turn, but then it continues straight because we're only following the right wall, as shown right here. Then the last thing it records is an S, and it records this when the robot moves forward a bit after a left turn. Now, this is really crucial to the algorithm because what this lets us do is distinguish between these 2 parts of the maze right here. An L followed by an S and an L means we enter in one way and then come out through a different path, where if we have 2 L's, that just means we've essentially turned around. And so how does the algorithm work? Well, first I have this sample maze here. This S will be where the robot starts, and we'll say this blue star is the object. This red path here is the path that the robot will take getting to the object by following the right wall, and the green perpendicular lines are where it detects and ignore. And this up here is the decisions array that the robot would put out when going through this maze. And so how does the algorithm actually work? Well, it will manipulate that array until it can no longer make any more changes. So first, every double L is translated to a B, which stands for back. As I explained earlier, if we have 2 L's, we know we've essentially reversed. And then after that, it removes all the S's, because this is all we needed the S's for, to distinguish that from whether we're just going up, turning left, going straight, and then going up again, or if we're reversing. So this is that same maze, and this is what the decisions array looks like after those 2 steps have been done. You see there's no more S's, and now there's some B's in there. So after that, sort of the main part of the algorithm is it goes through these 10 sort of equations, I guess, until it can no longer make them anymore. One of them is actually incorrect, but I'll get to that later. These 9 are the ones that are correct. And so for the first one here, LBR equals B. So we go left, we go back, and then we go right. Now they're kind of like functions where given one input, there's only one output. We know if in the array we have LBR, we know for certain it will look like this section of a maze, and so we can say that, okay, this is essentially a B, and we'll cut out that dead end there. And that's the same for all of these 9, where given this input, we know there's one output. And you'll see some E's in there, and that's because right here, if we have R, B, R, we set that to an E. And an E stands for we've traveled through there, but we're treating it as an ignore. So for the purposes of the program, E's and I's are essentially the same, but this helped me distinguish exactly what to do while coming up with this program. And so here we have the maze before and the decisions array, and now I'll go through the first iteration of the program. You'll see some of these dead ends like right here, they're going to get cut off. First I'll just gray out everything that the robot doesn't see to make it easier to look at. And so now you'll see the dead ends be cut off a bit, and this is what it looks like after the first iteration of the algorithm. And down here, this is that situation kind of I explained earlier that doesn't technically work, but we're doing it for the purpose of this maze. And so it'll go through this over and over until it arrives at this. And once it gets here, it realizes it can't make any more changes to it, and so it says, okay, this is the fastest route from the start to the object. Well, we actually want to get out of the maze, so what we do to get from the object back to the start is we just flip the array, and then all the L's are changed to R's, and the R's are changed to L's, and that looks like this. this right here is the fastest way out of the maze from the object. And so going back to that situation earlier where I said it's not technically correct, that's right here, I-L-L-L-E-R. For that maze, we set it to a back. That's not actually correct. And that's because, as explained earlier, those simple ones, they're like a function. Given the input, we know what the output looks like. But for this, given the input I-L-L-L-E-R, there isn't one unique output. This loop here is I-L-L-L-E-R, but so is this section of a maze right here. That's not a loop. So we can't say for certain that this right here we can just cut off. And this is a problem with almost every loop. There's always multiple sections of a maze that will give us the same decisions array as a loop would. So how would we solve this? Well, we have to start introducing a new variable that we record, which would be the distance between our decisions here. So if we have the distances here, A, B, C, and D, if we see that A is equal to C and B is equal to D, then we know it is a loop and we can cut it off. For here, B is kind of equal to D, but A is not equal to C, so we know it's not a loop, and so we can't just cut this off and set it equal to a B. Now, how it will look like in the decisions array, well, if the loop starts with a right turn, the array will look like R, L, 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 I, and in between those characters, there's an indefinite amount of I's and E's, depending on branching paths in the loop. It'll look the same with a left turn when it starts. But this actually doesn't cover every loop. There's still some, like, if we enter in the middle, what we'll have to do, we still only need to take the distances between our decisions, but we'll need to add certain distances and compare. See here, for this loop, we'll have to add distances A1 and A2 and compare that to C. And there's still more cases of loops that this won't actually solve. But what we can arrive at is a different solution where we can set up a coordinate system for our robot, and we know which direction it's facing and the distance between our decisions. So at every decision, we can give the robot a coordinate point for that decision. And then if we ever return to those coordinates, we know wherever we traveled is not needed and can be cut off. And that's the end of my presentation. Does anyone have any questions?